Hi again, more organic chemistry, and today I would like to show you an example that you might see on an upcoming exam dealing with the conformational analysis of cyclohexane. Okay, so in this example problem, it's asking us to draw the most stable conformation of trans 1-bromo 2-chloro cyclohexane. There's a couple strategies you can think about using. The first one I like to think about doing is just draw any structure of the molecule. Again, I'm more visual, so I'm just going to draw a normal skeletal drawing of cyclohexane. And then on carbon 2, put a chlorine, carbon 1, put on a bromine, and do it in a trans fashion. So I might, step by step, what would I have done? I've already drawn cyclohexane, so I might put on the 2-chloro group. So I get to pick how I want to number it. When you draw it, you pick. I'm going to let number 1 be up here. I'm going to go clockwise. You do not have to number it this way. Anything will work if you're drawing it. On carbon 2, I'm going to put a chlorine. And on carbon 1, I'm going to put a bromine. But now I have to do trans. So to show cis and trans with the skeletal drawing, one way is use dash and wedge bonds. And essentially, you get to pick. For trans, I need one of these atoms to be above the ring, another one to be below. So I'm just going to pick. I don't have any other information, so I'm going to let the bromine be towards us on a wedge, and chlorine's going to fade into the distance on a dash, and there we go. There's my drawing. And it turns out this is not the answer. I might give you a pity point saying, good job, you know how to draw from the chemical name, but you're not giving me the right shape, the right conformation. For that, you need a chair drawing. So to get the right shape, to illustrate the right shape, you can either use a Newman projection, which you don't want to do with cyclohexane. It's very complicated. It's possible, though. In a previous slide, it did show you a Newman projection of cyclohexane. But a better way of doing it is just drawing the chair conformation. Okay, so I jumped the gun there, right? So there's several shapes of cyclohexane, as we saw in the last video. There's the boat, twisted boat, half chair, but the chair conformation is the most stable of those shapes, of those conformations. So we know it's going to be chair. We just don't know which chair because there are two. So if you go to the last video, you can see how you can draw a chair conformation, and you can make it a little better. Right? Work in pencil or something that's that you can edit. Start with 2 parallel lines as I did, 2 more parallel lines, and then close up your ring again with parallel lines. So this line has to be parallel to this line. There we go. And maybe I'll go grab the eraser and clean up this little bit of bond that I kind of overshot. There. Okay. Yeah, depending on your level of perfectionism, I got it pretty bad. You can leave it. I'll leave it. Good enough. Well, at least for the carbon atoms. So let's draw in the answer. Okay. What we have to remember is when we're doing conformational analysis of cyclohexane, it's going to be a chair drawing. Which chair? It's going to be the chair conformation that puts the biggest groups where? Axial or equatorial? Equatorial, right. So let's draw equatorial bonds. Why not? Now, because that's where why not? Well, yeah, why go through the extra work of putting in the axial bonds? We're not going to put groups there unless we have to. So let's see. Where's carbon 1? Let's just start with that. You get the pick. I'm going to choose carbon 1 to be over here. It's at the top of the peak. The axial bond is going to be pointing straight up. Equatorial bond is off to the side, but slightly down, away from the axial bond, and parallel to at least one other bond. this one. And I just said that's going to be carbon 1. So that's where bromine is. It's 1 bromo. Where's 2? You get to pick when drawing, so you can call this carbon number 2 or this one number 2. Your choice. For me, I'm picking this one. There's more room. It'd be easier to draw. Let's see. Carbon 2 here is down in a valley, so the axial bond's pointing down. That means the equatorial bond is going to be pointing up. It has to be parallel to this line. Whoops, that's not very, that looks too horizontal. So let's try again. Wow, why am I doing it bad? My turn. That's going to have to be good enough. That's what chlorine goes. Last thing, let's double check, make sure we drew it correctly. Trans, 1 bromo, 2 chlorocyclohexane. So this is carbon 1. There's 2, 3, 4, 5, and 6. Sure, carbon 1 and 2 have bromine and chlorine. Good. Is it trans? Well, you can see that bromine is pointing down and chlorine is pointing up. Okay, I know on my drawing over here, I got the opposite. So really, this molecule is going to be, the bromine is down and the chlorine is up. Now, these two drawings are more similar to each other. I don't know if you can do this in your head, but if you go to the other side of the computer screen and view this, I know that's not easy to do. The chlorine will actually be coming out towards you. The bromine will be going away if you're on the other side of the screen. This places both groups equatorial, and that's where the bulkiest groups should go if you want the most stable. And we do, the most stable conformation. We're done. Okay, that wasn't too bad. That's a different question. Draw the most stable conformation of cis, 1-ethyl, 2-isopropyl cyclohexane. So let's take the same strategy. Let's just draw a quick skeletal drawing. Call this carbon 1. We'll put an ethyl group out there. That's 3 carbons, sorry. 2. Why do we keep doing it? 1, 2 carbons out there. On carbon 2, I need to attach isopropyl. Well, propyl's 3, and isopropyl is where you connect to the parent chain through the middle carbon of those 3. So here's my isopropyl group, there's my ethyl. I want to connect them in a cis fashion, which means my bonds either have to be both wedge or both dash. You get to pick. I'm going with both wedge. Here we go. Could have also done it this way. There we go. They're both cis, 1-ethyl. Yep. 2 carbons out there, 2 carbon branch. 2 isopropyl, 3 carbons out there, but connection through the middle carbon. Good. Let's get the most stable conformation. You need a chair. So let's draw a chair. Got my parallel lines, making that parallel, and then this one kind of parallel up there. And go get my eraser and clean it up. And not be too picky about it. Okay, now take that one back. Oh wait, I said I wasn't gonna be picky. Sorry. Okay, we want these equatorial. So, right, because that's the most stable. So I'm going to choose this to be carbon 1, this to be carbon 2 again. Ethyl, okay, so I need to find my equatorial bond. Pointing up is axial. So the equatorial bond's out to the left, a little bit downward till it's parallel to this line. Okay, so this is the first carbon of 2. So maybe I'll draw it like that. There's my 2 carbon branch, ethyl. That's carbon 1. Here's number 2. Okay, the axial bond is pointing down. Equatorial bond is going to be up. Parallel to this one, so that ain't too bad. And this is the first carbon of isopropyl. Two more. That. There we go. There's isopropyl. Cool. And then let's check the answer. This is the most stable conformation for an ethyl and isopropyl on cyclohexane, right? Both groups equatorial. This is carbon 1, 2, 3, 4, 5, 6. Good. Ethyl has a 1. Carbon 1 has an ethyl. Carbon 2 has an isopropyl. Is this cis? Well, this bond is pointing down. This equatorial bond is pointing up. Wait, they're opposite. This is trans. I'm not going to get full credit. I was supposed to do cis. You can't have both groups equatorial and be cis if those groups are on carbons 1 and 2. So no. Nope. That's not good. Try again. Draw my chair. That looks bad. Try again. That's better. That is bad again. You know, you think after all my years of practice, it'd be better. Well, give me a chalkboard or a whiteboard. I can do a much better job. That's my problem. All right. Got the chair again. This is carbon 1. Here's carbon 2. I need both of these to be pointing up. The only way for them to be on carbons 1 and 2 is somebody's got to take the axial bond, the crowded axial bond. So I want the most stable one. So which one is the least harmful? Which is the smaller group, ethyl or isopropyl? Isopropyl has 3 carbons. Ethyl only has 2. So I need the biggest group, equatorial. So isopropyl, you stay where you're at. I want the most stable structure. So on carbon 2, isopropyl, you hang out equatorial. You're the largest group. You get the most room on the equatorial bond. And then now, what goes up is the ethyl group. There we go. There's a cis, 1 ethyl, 2 isopropyl cyclohexane. There we go. What if the question also said, after you draw the answer, and draw the chair flip? I don't know why you'd have to do that, but maybe the teacher just wants to make sure you know how to do a chair flip. Or maybe you accidentally put the isopropyl on an axial bond and you put the ethyl equatorial and you don't have the most stable conformation. So then you have a chance to fix it. So what do I need to do? Well, first, to draw the chair flip, I can't have the seat of the chair going up and to the right. I need it to go down and to the left. There we go. Let's go down, let's go up. Connect them, make sure this, every new line has to be parallel to one other line. Ain't too bad. Cool. Now, careful. You can't just, I know you're drawing it, you get to say where it goes, but you've already locked in your choice by drawing this one over here. You already put the ethyl group on the axial bond, and the ethyl group is on the far right, that's left, far left carbon. And you already numbered the ring. This is carbon 1, that's 2, 3, 4, 5. So because you chose, I did this time, but when you draw it, you drew one chair already. Now you're locked in. You must flip this structure correctly to get the right flip. Now, some of you might want to go back and look at the animation and just watch. I mean, it's helpful to see, okay, I'm going to go back to that YouTube video and, you know, fast forward the video to I'm at a point where on the left, this carbon is the head of the chair with the hydrogen axial. Play the video and see where it goes. You'll see that this carbon will go from the head of the chair to the foot. So the ethyl group is going to be attached to this carbon. What's next? Well, the ethyl group used to be axial, so now it must be equatorial. So let's draw the equatorial bond. Well, where am I? I'm in a valley or on a mountain peak. This carbon's in the valley, so the axial bond points down. Equatorial bond starts horizontal, but moves away from it, goes up until it's parallel to the C in this case. So my ethyl group starts here, and the word foot is in the way. Let's get rid of that. That's good enough. Okay, 2 carbon attached to carbon 1. Good. All right. I got the ethyl group. Now it's time to draw the isopropyl. Carbon 1, 2, 3, 4. I'm going around the ring. Looks like counterclockwise. You already numbered this first. I did, I know. But when you're doing it, if you put ethyl here and isopropyl there, you have numbered the ring counterclockwise. You got to stick with it. This is 1, 2, 3, 4. Whoops. Go back. More, please. That was 4. This is 5 and 6. So here's carbon 2. That's where you have to attach the isopropyl group. Isopropyl used to be equatorial. In the flip, it's going to go axial. So where's my axial bond? Well, I'm on a mountain peak. So I'll be pointing up. I'm going to squeeze it in here. Another option is to make the line go through that bond. So you can draw that isopropyl group up here. I think I have enough room. Let's see, axial, let's see, equatorial bond was pointing up. It still points up. That's the other way to remember. And then isopropyl is where this carbon's the first carbon of the isopropyl group. I got methyls on either side. There we go. Hopefully that's clear. I'm done. And then if the teacher says, well, how come the chair on the left is more stable than the chair on the right? You could say biggest group. Now I do want to scroll down a little bit, get a little more room. I should have said isopropyl. The biggest group, isopropyl, is axial. This creates more 1,3 diaxial interactions, if you want the scientific term. Than ethyl. Isopropyl is bigger than ethyl. This molecule would prefer to put the biggest group back equatorial. This side is more stable. This is a more stable conformation, a more stable shape. Cool. What I failed to remember to tell you is that up here, what if we were asked to draw the cis? Then you want to put the bigger group equatorial. Okay, so who's bigger, bromine or chlorine? Well, you should be getting a periodic table on all your exams. So go find bromine and chlorine. And as you go down the table to get bigger, if you forget that trend, just look at the number of protons, which should approximately equal number of electrons. If it's a neutral atom, it does equal. But bromine has 35 electrons in a neutral atom. Chlorine only has 17. More electrons mean more shells. Electrons repel, they need more room. Bromine is bigger. Cool, okay. So we talked about how to draw. This was a nice review. From the name, we got this my skeletal drawing, and then we went to the chair. And then by knowing that equatorial bonds are better places to put the bulky groups, we could draw the most stable conformation. Whether it was trans for 1,2 groups, very easy. But sometimes you're forced to draw the cis or the trans, which depending on where the groups are sitting on the ring, you might have to have one group axial, one group equatorial. And you want to put the biggest group equatorial to make it more stable. All right, last idea, a little justification. How come we're doing this? Does it really matter? Yeah, here's an example where it matters. So take a look at this structure here. This is a repeating structure, a polymer. This is actually two biopolymers, biological polymers, that are better known as starch and cellulose. Turns out this repeating unit is glucose. That's blood sugar. And if you connect, well, if you connect blood sugar end to end in this fashion, you make starch, which is a great food source. It's found in potatoes, corn, and wheat. It's not that water soluble, but much more water soluble than cellulose, which is also made of blood sugar. Connecting blood sugar end to end this way makes for the material found in paper or cotton. Wood is about 50% cellulose. That's a much different material than starch is, right? Cellulose is much less water soluble. It's not easily hydrolyzed or broken down, right? It takes a long time for wood to rot, but you leave your potatoes outside for overnight, you know, they're going to be rotting pretty quickly. They decompose, hydrolyze easily. What's the difference? They're both made of blood sugar. Well, right here, what kind of bond is that? This bond right here. Well, look at the ring. Hey, that's a chair conformation. It's not cyclohexane because there's an oxygen instead of carbon in the ring, but it's the same shape as the chair conformation of cyclohexane. We got an axial bond. And all these glucose molecules have one of the oxygens on an axial bond. Whereas for cellulose, all of the bonds are equatorial. That's the only difference in the chemical structure between starch and cellulose is an axial versus equatorial bond. That makes a world of difference. You know, chew on your shirt. This is a cotton shirt. That's blood sugar, but I can't break this down because my body doesn't have nature's catalyst enzymes that can break this equatorial bond. You and I have enzymes that can break down the axial bond in starches, however. Yeah, pretty cool. All right, that's enough for now. I'll see you next time.